Hey there. Uh, Hello there. Hey there. In the last video, we talked about representing an unweighted and undirected graph using the edge list representation inside your machine. Now let's talk about how to do that exact same thing with undirected weighted graphs. Okay, so what you're seeing on the screen right now is basically the last diagram that I drew on my previous video, where we talked about how to represent unweighted, undirected graphs in the machine. You don't necessarily need to watch that video to understand this video, but you probably want to watch a few of my other previous graph videos to know the basics of graphs and edge lists and edge-based paths and node-based paths and all that stuff. So for now, I'm just going to continue from this document. So let's see. I'm going to duplicate this real fast. I am going to just kind of modify the captions here because we're not going to do unweighted anymore. We're going to say a weighted undirected graph. Did I get that backwards? I think sometimes people say undirected and then the weighted part after. So I'm just gonna change it. So it's still undirected, which means the edges don't have arrows, so that's fine. But it's going to be weighted now, which means I have to assign a cost of traveling along every single edge. So I am going to just sort of like erase a bunch of this stuff real fast. Erase these notations. You know what? I'm going to erase all of this because I want you to, see it from start to finish. Okay, so now I'm going to add weight costs on every single edge. In the last video, what I mentioned is that the edge list representation of a graph in the machine is basically your graph is a tuple. That's the orange, markings up here. Your graph is a tuple where the tuple consists of a vertex list and also an edge list. So we'll do that from scratch together again, but let me get the weights on there first. What color do you want? I don't know. I'm going to put arbitrary numbers on all the edges just to say that every edge has a cost. Remember, in a graph, when you travel along an edge, if the edge has a weight, then you consider that weight to be part of the cost, usually, of traveling there. So like if this was a network diagram, maybe these weights represent pings or lags or bandwidth cost or something like that. If this is like an airport diagram, maybe the weights represent gasoline or time or something like that. So I'm going to do like 4 there. We can repeat weights if we really want to. I'm going to line this up a little bit better. That 12 looks gross. Okay, I think we're okay now. At 14. All right. Did I forget anything? Raise your hand if I forgot something. Oh, I forgot. Okay. Did you raise your hand? Okay. I'm going to do the 13 and 6. Let's just put a 2 weight there. You could put 1s everywhere if you wanted to. I mean, any number is fine. Also, in an unweighted graph, you kind of can consider the number of hops to be a path cost, which means you can kind of consider every edge to just have a weight of 1. But for now, we're just going to say this is the weighted graph. Okay, so the first thing we need to do after that is make a vertex list. So our vertex list is just going to be a list of all of our vertices, all of our nodes in the graph. How do we list them? So for starters, like we usually say vertex list, but for me personally, this particular data structure just that we're going to type up on the bottom, I usually like to consider that a vector or an array at least. Because you can jump into a specific index in constant time, which is really, really fast. If you don't know Big O and time complexities, check out my other videos. But it's just really, really fast to jump to an index when you're using an array or a vector. But it's kind of slow when you're using an actual linked list or some other data structure that makes you scan through it. So I'm going to say that my vertex list is actually a vector, but I'll keep calling it a list. Anyway, so we got the vertices, we have to start naming them. Okay, so the first thing is I'm going to do, we got the 3 there, and we got the 13, and we got the 6, and the 12, and the 15. I'm just naming all of the nodes in my graph. I like to go from left to right because that makes it easier for me to debug what I'm doing. You probably, in your code, I said this in the last video, you probably don't want to store the actual value in your vertex list. You probably actually want to create an object of type node or of type vertex and give it the template data type of, in this case, integer, and then set the 13 inside of the class. It's not as fast and memory efficient as just putting a number there, but for me, I like more flexibility, and I like to be able to do more powerful things with my stuff. So I'm going to say that 13 and all of the other nodes, really that represents to me I made a brand new instance of a class called node or vertex, and then I set it up however I wanted. And one of the things I did to set it up was stick the number 13 inside of the class. But for the diagram, it's fine like this. Okay, so we have our vertex list. That's the V. If you're looking at the the V comma E, the V part. Now we need to do the edge list. So I'm going to say, here's my edge list. And we're going to use the edge list representation like I talked about in previous videos, which is basically a tuple where one tuple describes one edge. So in our graph that we have right now, we definitely need a starting point and an ending point. So let me just start by looking at the 3 node, and I want to describe one of the edges for the 3. So the 3 goes to the 18 and the 13 and the 12. I'm going to scan my eyes from left to right to make it a little more simple. So the 3 node, it connects to the 13 node. So I'm going to put a 3, 13. The order of the nodes doesn't matter in an undirected graph. So I could have easily put 13 and 3. It's fine. You don't want to duplicate it by putting 13, sorry. You don't want to put 3, 13 and then later put 13, 3. You don't want to double it up because that would be like representing 2 separate edges. I'm just going to sort it in my mind before so that I don't have to sort it again later when I'm reading the graph, which makes it faster for read operations. But so 3 goes to 13, and then we have to represent the weight. So the tuple gets a little more complicated than the last video, just by a little bit. I'm going to say 3, 13, the weight, which is just a 1 here. And I think I mentioned this in my other videos like a while back, but the weight doesn't have to be integer. It could be a float. It could be any data type you wanted, really. As long as your algorithms support it and you have, your operator overloads all done and all that. It could be a full class just for the weight if you wanted to. But for this video, it's just going to be the weight is an integer, so that's the cost of traveling along that one edge. So notice how all of our tuples have 3 items each. It's a triple tuple. So I'm going to continue trying to represent what the 3 touches. So the 3, it touches the 13, and it also touches the 12. So I'm going to say 3 goes to 12. What does that edge cost? It costs us 6, because that's the little pink 6 there. We're done with that tuple, so what else does 3 touch? It touches the 13, and then it touches the 12, and then it touches the 18. So I'm going to put an 18 there. What does that edge cost? It costs a 4, because there's a pink little 4 at the very top of the graph. Surprised you didn't know that. Okay, so then, I'm sorry. We're going to move on to the next node. So we did the 3 already, so I'm done with that. I'm going to look at the 13. Where does the 13 connect? It connects to the 3, but that's to the left, meaning, because this is why I like to scan my eyes from left to right. I already know stuff on the left is handled. I don't have to do it again. So forget about the 3. I already described it up here in the very first tuple, 3, 13, 1. I don't want to describe it again. So forget about the 3. Now the 13 connects to the 6, so 13, 6. And what does that cost? It costed 2 for our arbitrary labeling. 13 doesn't touch any other node, so we're done with the 13 row. And by the way, I'm doing new lines here. You don't have to do that. I like to do one, row per start node to make it look cooler and nicer. Okay, so the 13 is done. Now let's do the 6. 6 touches the 13, but remember, in the previous row, we just handled that, so I'm not going to do it again. The 6 to the right touches 3 other nodes. You can see there are 3 lines protruding on the right side of the 6. So I'm just going to take those from left to right. It's touching the 12 at a cost of 14. The 6 is also touching the 15 at a cost of 12, I think. And the 6, if I make mistakes, just leave it in a comment. I will leave the video up so you can always remember my humiliation, but I'm going to try my best. I did not practice this. 6 touches the 15, and then the 6 touches the 18. So 6 touches 18, and then it costs 9. So now we're probably done with the 6. Moving on, one node to the right now. We're going to look at the 12. Okay, so the 12, it touches 3 and 13 and 6, but those are already handled, so forget it. The 12 touches the 15. We did not handle that, right? Yeah, because we're going from left to right. And then it costs us from going from 12. What am I doing? It doesn't touch the 15. Oh my God. So the 12 touches the 3, which is already handled, and it touches the 6, which is already handled. And then it only goes to the right to the 18. Okay. Well, anyway, You know, when I make mistakes on camera and I say do over, I always go, I don't know why. So the 12 and the 18, it's going to cost us 3. So then we're done with the 12. So I'm going to go to the next one. Oh, we'll look at the 15. The 15, 6 is already handled. 18 is not handled yet, so I'm going to put 18 there. It's going to cost us 88. And then the 18 is the last one. There's nothing to do because every node is on the left of the 18. If you pause the video and look at every single node, you'll see it's already represented in a previous node. So we're officially done with the basic edge list representation of this graph, this undirected but weighted graph. We need to do something else though. I mentioned in the last video, I'm going to repeat it in case you didn't watch the last video, but we need to make sure that, oh, I guess I forgot to separate those two things. That means I have to duplicate the vertex list over here on the right side too. Okay. So on the left, this is okay, but it's kind of slow because what if we're trying to look at, you know, one particular edge? Let's say that we want to see what's going on with this this edge right here. Let's say the 3 and the 13 edge for whatever reason. I don't know, green, 3 and the 13 edge. Okay, so we're looking at that edge. Maybe for some reason we had just finished scanning. Maybe that's not a fun edge. Well, what's going on? Hello. Oh, I forgot to set up a thing where you can make your cursor really visible. Okay. Actually, so this is not the most fun edge. Let me see about the 15 and the 18 edge. Excuse me, I had to take a drink of water. So we're going to look at this edge connecting the 15 and the 18 node. That's a little more interesting. So you can imagine maybe you were doing a little scan. If you know Big O complexity by now, we had to check out every single edge in this edge list until we found the one that connected the 15 and the 18. So this was a linear time scan based on the number of edges. So this is just, it's scalable, but it's not very fast, right? So we ended up kind of looking at this one right here. Not fast. But what if we want to examine some properties of the nodes or the vertices involved, like the 15 and the 18? Here in this representation on the left, we have the values. We have the 15 value and the 18 value. We don't really have a pointer to a full node object if that's what you're doing in your code. So how do we get those node objects? We're going to have to do another linear scan. We're going to have to look at this one right here. Oh, that doesn't match the value of 15. Look at this one. Look at this one. Look at this one. We're going to have to scan every single node until we realize that it's those two at the end. This is true even if it's a vector holding your vertices, because if we don't know the index, then we have to actually just sweep through the whole vector. So that's really slow. It's still kind of scalable, but it's not the best. Instead, let's update the representation on the right to have indexes. We did this in the last video, but basically if you just kind of look at this 3 node here, the 3 node, well, let me copy this one more time. The 3 node corresponds to index 0, which I forgot to write down. My bad. Let me write that down for you real fast. Get rid of that. Get rid of that. Get rid of that. Okay. So I'm just going to update this vertex list to just show you that if we have a vector or an array, then every single item has an index. Here's index 1, index 2, index 3, and 4, and 5. And then I guess I'll just copy paste that to the other one, since I was too dumb to make an extra separated graph there, separated item. Okay, so the 15, sorry, no, the 13, the 3 and the 13, I guess I got to get rid of that. That's distracting me. The 3 and the 13, those correspond to indexes 0 and 1 in the vertex list, right? So 0 and 1, that's the 3 and the 13. So I'm just going to change the values, the t-type values, to the raw indexes. It's going to seem a little weird at first, and I'm going to leave the weight alone because that's totally fine. We're not going to jump to a weight unless maybe you had a weight list, a weight vector. If you wanted to make instances of weights, you could do that. I'm not going to do it. So then again, the 3 is a 0. The 12 is index 3. The 3 is another 0. The 18 is index 5. I'll just do this for every single row. So the 13 here is index 1. And then the 6 is index 2. Notice how I'm just looking up here at the indexes of the vertex list. And I'm just changing the node values to the indexes where the nodes actually are in the vertex list. So that's a 2. and then the 12 is going to be a 3, and then the 6 is also going to be a 2, and the 15 is going to be a 4, and then the 6 is going to be a 2, and the 18 is going to be 5. On to the next row. The 12 node is index 3, the 18 node is index 5, the 15 node is index 4, and the 18 node is index 5. So, whoa. Correct me if I made a typo in the comments, please. I'll release another video as a thank you. But now I've converted the whole entire representation on the right side to an index-based, edge list. So I'm going to do this one over here is by value, and the one on the right is by index. Why is the one on the right better now? Remember, at some point we might have been scanning to find an edge. Whoa, what did I just do wrong? Oh, I clicked over there. Okay. We might have been scanning to find, some edge. So we're like scanning, and then maybe we decide we're trying to figure out what's going on with the 2 and not the 2 and the 4, the 6 and the 15 node, right? So that's the 6 and the 15 node. That's basically, this right here. So now what if we want to do something with the nodes? We want to do something with the 6 node, do something with the 15 node. We don't want to scan through the vertex list again. We don't want to go scan. That's linear time. That's not as fast as it could be. So instead, we've already converted here so that we have indexes. So if I look at the 2 and the 4, the 2 and the 4 represent indexes, not node values. So this 2 tells me that I can go to index 2 to get the 6 node. And the 4 tells me I can go to index 4 to get the 15 node. Notice how I did not have to scan the vertex list to figure out where those nodes are. And if you're using a vector for your vertex list, then you can jump to every index in constant time. So now, if we were going to, search and do a bunch of stuff on edges, we probably only had to spend linear time on the edge list, but then we only spent constant time to manipulate each node, whereas it would have been linear plus linear in the past. Like on the left side, that would have been if we're going to do stuff with both the edges and the nodes, it would have been O of linear time based on the number of edges. If we're going to do something to every single edge, plus linear time based on the number of vertices. But over here, it's going to be linear time of the edges plus just constant time, which basically means it's going to be, big O of just the number of edges. And I'm talking about a fantasy scenario where we're just going to scan a bunch of stuff. You can imagine there's a whole bunch of different operations you could do on a graph, and it would be very advantageous and fast if you could just jump to a node if you wanted to be able to manipulate it directly. Let's see. So I think 20 minutes already. So I think this is going to be it for today's video. And I'm going to do another video after this where we start working with directed graphs. So I'm going to do directed unweighted and then directed weighted. So by the time you watch all 4 of these videos, you'll know how to represent all 4 types of graphs in the machine. Okay, anyway, so thank you for watching this video. I hope you learned a little bit of stuff and had a little bit of fun. I'll see you next time. Tell your friends. Eat a chocolate. Okay, I'm outie. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all.